Thanks everyone for coming to today's Biogeochemistry Science Friday. We're lucky today to have a presentation from Dr. Lingcheng Li from Pacific Northwest National Laboratory, and he's going to talk to us about a machine learning approach targeting parameter estimation for PFT coexistence modeling using ELM-FATES. Go ahead.
Let me see my screen. Yeah, thanks for the invitation and thanks for the introduction. So today I will talk about how to use the machine learning to targeting the parameter estimation for specifically for the PFT coexistence modeling in ELM-FATES. So first, I would like to thank all my co-authors to contribute to this work, and also thanks for the in charge of this project and funded by DOE. And so tropic forest dynamics is, as we all know, that generally is very important for our global carbon cycles. And generally, it is about 25% of the carbon in the tropic forest, kind of 25% of carbon in the terrestrial biosphere, and about 1/3 of the it absorbs 1/3 of the terrestrial native primary productions. And the recent study also shows it is very important, but it is also vulnerable. Recent study has shown that in the tropic forest, the resilience is decreasing due to the water limitations and also the climate variabilities. So, and also in the under climate change, studies have shown that more stress for the tropic forest, like climate change induced drought, fire, extreme storms, and also from human beings like deforestation. So to better understand how the forest dynamics under the climate, so we usually use the dynamic vegetation tool to simulate the forest dynamics. So what kind of tools we use? So generally, we have 3 types of dynamic vegetation tools. One is traditional digital dynamic global vegetation model, and another is forest gap model. Let me show you here. Yeah, and also the cohort-based models. So compared with the traditional DG VMs and the forest gap model, cohort-based model is usually have advantages like it can represent sufficient ecosystem dynamics, but also it can maintain relatively high computational efficiency. So here I will show you examples like how they are different. So for the traditional ELM, so this is traditional DGVMs. So you can see that at each grid cell, you have different PFTs, but each planet function types, they are isolated with each other, not directly have competition with each other. So this is not realistic in our tropic forest. But in the cohort-based DGVMs, so it has the in each of these classification of cohort, it had different planet function types. So these different planet function types can compete with each other. So this is more realistic to represent the forest or ecosystem dynamics. So ELM-FATES can represent this different PFT competitions. This is its big advantage, but its big advantage is also a big challenge. So the challenge here is how to reasonably simulate the coexistence between different planet function types. So based on the Lingcheng-based coexistence theory, if you need to have coexistence planet functional types or plants, first you need to ensure environmental filtering, so which means you have the convergence in strategy to adopt to the surrounding environment. So for example, tropical humid tropical forest, so you have trees species in the humid rainforest, but in the arid regions, you only can have shrubs and grasses. So for the trees, they have like they can adapt to humid environment. So this is the similarities, and for grasses, they also have some similarities to adapt to the arid environment. And the other part of the Lingcheng-based coexistence theory is Lingcheng partitioning. So you have some similarity, but you also show some difference for different species. For example, in the humid rainforest, some of the trees you can grow fast and grow tall. You can grow like you can in the canopy layers, but some of the vegetation species you can adapt to the understory. So they have some differences in their strategy to adapt to different environment. So how to based on this theory, how to represent like conceptually to build the model to achieve the coexistence. So generally, like in our model development, we need to represent a sufficient mechanism or process is to ensure like the vegetation to grow, and also within this process, we have like key parameters, and we need reasonable key parameters to ensure the coexistence between different PFTs. So for example, like in the ELM-FATES, we have vertical canopy structures. So this is the process we represented in the model. And also for different PFTs, so some PFTs more favorable in the understory, some is canopy layers. So how to show this difference? So we needed to represent the reasonable parameters to ensure that a difference in these vertical canopy structures. So today's my talk is like more focused on how to choose the reasonable tree parameter values to ensure their coexistence. So generally, like in previous studies based on ELM-FATES, they used a filtered ensemble approach to select the parameters. So basically first you generate an ensemble of parameter, and then based on this parameter ensemble to generate ensemble simulations. With these simulations, then you select out which run is have like coexistent PFTs. Then you filter it out. But this, for example, like in Huang's study 2020, they conducted this approach, and they conducted 70 times run one at a time experiments, but they only get one reasonable parameter sets. So it's about 1/70. It's about 1.4% of the experiments can coexistence. And our last study is for poverty 2020. So this also they conducted like two stages of the experiments. The first stage, they have about 0.3% is coexistence, but the second stage about 5.5 coexistence. So from here, you can see that generally this process is low efficiency and a low percentage of the PFT coexistence experiments you can get. So our study here is trying to solve this or alleviate this challenge by using machine learning technologies. Basically, we have two goals. Like first, we need to use machine learning technology to increase or to have more coexistent cases. How to have more coexistent PFTs in the experiments. The secondly, we want to reduce the model bias or errors against the observations. So our test bed is, our model is based on ELM-FATES, and our study site is at the Manaus tropical forest site here, and our data is from the flash tower from this data from this site, includes the atmospheric forcing, DGP, ET, suitable heat, and above ground biomass, generate water, energy, and carbon variables. So because we want to study the coexistence, so the basic like traditional or is to represent two PFTs, so you can compete with each other and you can start this how the response. So we represent two PFTs in the model, and this two PFT, one is early, another is late successional brownleaf evergreen tropical trees. And we represent two is like basically this early and late can represent a primary axis of the variability in the tropical forests. So you can hear like in early and late PFTs, and they have different trade-offs between their trees. Like for example, the Vmax, which controls the photosynthesis rate, Vmax of the early PFT is larger than the late PFTs, and also the specific leaf area and background mortality is also for early is larger than late. So which means generally, like if you have larger Vmax for the early PFT, which means can grow faster than the late PFT. But however, the early PFTs also have larger background mortality, which means it can easily die than the late PFTs. Here is the specific like parameters we choose. We adjust, we will calibrate or estimate 11 treat parameters. So include the Vmax, specific leaf area, background mortality, and wood density and leaf longevity, and also the carbon storage ratios. And all these like parameters will reflect the trade-offs between two PFTs, and all these ranges we based on the literatures where they measured at the tropical vegetations. And also we represent that the early PFT is relatively less resistance to drought compared to the late PFTs. So this why we represent here, because we want to study the drought event later. But in this study, this is not that effect much. So here is the overall flow chart. Generally, like we will use the get the parameter sampling. We use large hypercube sampling, and also after the sampling, we consider the trade-offs because as we mentioned, like for example, the Vmax of the early larger than the Vmax of late PFTs, and other trade-offs. And then based on the initial sampling, we will conduct different experiments. Like one experiment is control experiments. So another experiment, second experiment is the experiments with the consideration of observed treatment relationships. Then we will use these experiments to build the machine learning models, and then we will use the machine learning models to select the parameters. So here is basically the flow chart, but I will go through all this step by step. And during this, I will answer 3 questions. Firstly, one of my experiments is considering the observed treat relationships. So whether consider the observed treat relationships can improve the PFT coexistence modeling. The second question is like, can we build like very simple correlations based on our initial experiments? And how can this simple correlation can guide the PFT coexistence modeling? The third question is like, after we use machine learning, does machine learning really significantly improve the PFT coexistence modeling? So here is, first I will talk about 2 experiments. The first experiment is control experiments. So there are low constraints of any observations. So it's only consider the trade-offs between all between different PFT. The second experiment is experiment OBS. So additionally, this considers the observed treat relationships. And for each experiment, we run 1,500 runs per each experiment. And for each run, we simulate 350 years to reach equilibrium state, because like the model like this 300 years to stabilize the PFT competitions and dynamics. Then what kind of observed treat correlations relationships we consider? So one is like between the Vmax and background mortality. So this relationship is based on the measures from the COVID study. So we build a simple nonlinear equation to quantify the risk max and background mortality. And similarly, based on Logan's study, we built another two equations to consider how this specific leaf area index and the longevity of leaf that relationship between trees. So the second study is we will additionally add these informations from the observations. So here is the there are parameter distributions. So this is risk max and the specific area index. This two is generally similarly, and the blue color is for the control experiment. Red color is for the observe constrained experiment. But for the background mortality and the wood density and leaf longevity, there show a difference. So you can generally the observation constrained experiments have narrow background mortality compared to the control experiments, and also but it have broader wood density and also broader leaf longevity. Then let's look at how the simulation performance. So the similarly the same. The blue color is for the control run. The red color is for the experiments with consideration of observation constraints. So basically, you can see that the red color. So the x-axis is the relative bounce. If you more close to zero, which means better. So you can see that the red color of the observation constraint experiments is slightly close to zero or slightly better than the control runs. Similarly for ET sensible heat, and this is Bowen ratio, and for GBP and above ground biomass. And also you can see that for the above ground biomass, the observation constrained experiments have narrow distributions. So the observation constrained experiment just slightly improves the simulations, but for the coexistence, actually it's degrade the coexistence. So coexistence here, I quantify use the biomass ratio between the ELM PFT and the total biomass. So if we define three categories, if like 0.9 to 1.0, which means larger of the biomass is by the ELM PFT. So we define it as ELM. If this ratio between 0.1 to 0.9, we define it as coexistence. If it is 0.0 to 0.1, which means late. So which means larger of very small is PFT is ELM. So most of the PFT or biomass is from late. So this is if we see this ratio is more between 0.1 and 0.9, which means this experiment have more coexistence. So when you compare with the control run and also the observation constraint run, you can see that there's more. The blue color here have more counts or more experiments between 0.1 and 0.9. It has more coexistence compared than the observed constraint experiments. So in terms of the PFT coexistence, if you consider the observed tree relationships, it actually degrades the coexistence modeling. So why is that? So yeah, also like we cannot use the observed tree relation cannot improve the PFT coexistence modeling. So why is that? So we have like basically three reasons. So this is just some general reasons. So one is like ELM-FATES limitations. So its model itself is not perfect. Some process is not, for example, some process is not well represented in the model. So even you have the observed tree relationship, but still like cannot. But this observed relationship is not well represented in the model, and then you have like you have worse coexistence modeling. The second possible reason is that observation data limitations. So all of these, like when we build these correlations, relationships between the trees, these trees measurements is from the tropical forest, but it's from large scales. But for our studies, is at point scales. How the large scale relationships can represent the point scale relationship still may not right. So the third reason is like when you recall that the relationships between we used between different trees is relatively simple, even it has non-linear, but it is still simple. So this simple relationships can still is not perfect if you use this to constrain the observation, to constrain the modeling. Yeah. So in our following studies, in our following analysis, we only use the control experiments, which means we don't use the observe tree relationship constraint experiments. So let's look at the how the parameter space looks like in these control experiments. So yeah, this is not her figures here, not her plot here, but basic information from here is that you can see some first the orange color is the coexistence, and the blue or green color is early or late. So you can see that the orange color is in many spaces overlapped with these other early or late. But if we zoom in, like some of these still have some difference between them. So one basic naive idea is, can we build some simple equations or relationships to distinguish the coexistence between coexist and early or late? So I'm trying to do this. I find out that the three patterns have the most distinguished patterns between the coexistence and the early or late. Then let's look at the density function, density map. This is more clear. So we build three linear equations. You can see that. So the over these regions, the orange color is distinguished with the green color and the blue color, but still they have overlaps. But under these regions and these regions, they are relatively narrow. The regions will have coexisting cases, right? So if we narrow these cases, so you can still, one more thing is you can see the black stars here. The black stars means the optimal cases. The optimal cases, which means first the case or the simulation should be coexistence, and also the relative bias between the water, energy, carbon relative bias compared with observation should be less than 50%. So we build three equations. With these regions, we should have more high percentage of coexistence. So yeah, of course, the coexistence from the original 20% to 30% if we focus on, we constrain to these regions, but even it to 30%, but the only still 70% is still either only or late. It's not so larger of them still is it's not coexistence. It's not ideal. And then also if we consider the observation of the water, energy, carbon, if the optimal cases, the optimal cases still have only 2.3%. So it's still okay, it can give some, if we build this simple correlations, they have some guidance, but still have very limited guidance or very limited optimal cases as so this simple correlation is still not enough, but still not perfect. So we probably do not want to use it. Then how to do that? So now we have the control experiments, 1500 control experiments. We have the parameters of xn parameter and the difference, we also have the outputs from the models. So for example, we have this max, we also have the ET, and we have 1,500 pairs of this X and Y. So we want to build an emulator for different Y, and then we choose, like, we use the machine learning algorithm to build these functions and to build these emulators, and we use XBoost here. And then with these machine learning models, we can analyze to do the parameter sensitivity analysis to see which parameter, which traits dominant control the coexistence. And then we will use this machine learning model to select the parameter. If these selected parameters by the machine learning can improve the coexistence modeling. So here first, let's look at the performance of the models. So generally, we build 6 surrogate models for ET, sensible heat, Bohr variation, GBP, above-ground biomass, and biomass ratio. So this one is for the PFT coexistence quantification. So overall, you can see this is the x-axis is the ELM-FATES simulations. The y-axis is the machine learning predictions. Overall, it has a good performance, especially for the grid level variables like ET, sensible heat, Bohr ratio, GPP, and above-ground biomass. So all this is grid levels. But relatively above-ground biomass, especially for the coexistence or the biomass ratio, is not that good compared with other variables. Why it is not that good? Because this biomass ratio or PFT coexistence is very sensitive to different parameters, and it's relatively difficult to emulate. And also because we only have 1,500 samples, and in these samples, only 20% is coexistence. So relatively, we don't have much coexistence samples to train the models. So this is to relative bad performance, but it's still okay. Then we will, based on these 6 machine learning models, surrogate models, we conducted the sharp analysis, which is the parameter sensitivity analysis. So basically, the y-axis for different parameters, if you have a longer, larger values, long bars, which means more important. So interestingly, we have, for the grid level variables, ET, sensible heat, Bohr ratio, and GBP. So this grid level fluxes, only 3 features or 3 parameters are important, and all these 3 are the same, and they all are for only PFTs. So for the with max, special leaf area, and leaf longevities, and this is kind of reasonably. For example, you have the red color here means with max have positive correlated with the evapotranspiration. So if you have large with max, you have relative you can have more evapotranspiration, and you have more GBP. You can absorb more carbons. So this is for grid level, but for the other 2 variables, above-ground biomass and biomass ratios, these 2 variables you can see that more than 6 features are important. So which means these 2 variables are relatively difficult to emulate, or it's very sensible to many processes, especially for the biomass ratio. This 2 is is related to the competition between 2 PFTs. So, and also if you look at the parameters, the difference between the only and the late PFTs are important. Not like here, this is the only PFTs, the parameter is important, but here it's more related to the difference between the 2 PFTs. This is also kind of reasonably, because it's related to their 2 competitions. So the difference between the trees parameters becomes important. Then like we after we have the trained models, we want to use this to select the parameters. Basically, the process we will use, first we generate the sample parameter ensembles, then we will put it send it to the machine learning model, then we get the simulated all these 6 variables, then we will filter this ensemble of the result, and then we will select out also we select out 1,500 ensembles that can have reasonably small model bias and also have the PFT coexistence. And then we will send these selected parameters to the ELM-FATES model. We will run the model and get the result, and then compare, okay, if our selected parameters can get more better result. So here is the select parameter space, parameter space. Yeah, this is too many plots, but one point I want to mention is that all these parameter space can capture the if you remember that I tried to build a simple correlations based on the control experiments, and but it's not good enough. Our machine learning selected parameters can capture these correlations. So at least the machine learning model learns the simple correlations from our visualization analysis. And then when we compare our machine learning selected parameter with the control experiments, you can see that there are consistency between the green color and the yellow color, orange color. The green color is machine learning selected parameter. The orange color is the coexistence parameter from the control experiment. So they show some consistency. So which means machine learning try to find the parameters within the coexistence cases in the control run, but they also have differences. You can see the machine learning select parameter have smaller VC max in the early and late PFTs compared to the its training data or its control experiments of the coexistence experiments. So let's look at the result. So we send our machine learning select parameter to the ELM-FATES model, then we get the simulation result. So the left figure here is model bias, and the right figure is the coexistence analysis. So first, let's look at the model bias. So the blue color is the control simulation, control experiments, and the green color is the FATES simulations by the machine learning selected parameters. So generally, you will see that the relative bias is for the green color is more close to 0 or is smaller than the control experiments. So which means it improves the simulations in terms of model bias in the water, energy, carbon, and a background biomass. And you can also see that the control experiments have very large range, but the machine learning selected parameter FATES simulations have small, narrow range. And especially when we look at the coexistence, you can see that before you have large proportion, large percentage of the simulations in the only ratios. But now when you look at the machine learning selected parameter, you can see that most of them is within the coexistence range between 0.1 to 0.9. So which means like machine learning select parameter do largely improve the FATES simulations. And if we look into more details about the values, like for the coexistence cases, the machine learning selected parameter is increased like from 20% to 70%, which means it improved 3.6 times more coexistence cases than the control experiments. And also for the, if we filtered these coexistence cases to get the optimal cases simulations, which means we further consider the less model bias. So in the control simulations, only 1.4 cases like it's optimal case, optimal experiment. But now we have about 30%. So this improvement is more than 20 times. Yeah, here is like we look at how the machine learning select parameters space looks like. So after the simulations, we can see the yellow color is coexistence, and the other two colors for either early or late. So you can see that the yellow color is mostly like overlaps with either green color or blue color, which means from our visualization analysis, we cannot distinguish like either coexistence or early or late. So which means like there's low sample correlation can build to distinguish coexistence from the early and late. So which means, yeah, it's considered better, yeah, than our visualization analysis. And then this is the selected optimal cases, and you can see that the red color is the signal cycles of the ELM-FATES simulations by using the parameter from the machine learning select parameter, and the black color is for the observations. So generally, it captures the signal cycles, but still you have some differences. But generally, it's capture that. Then the last point I want to mention is like what can we learn from here? Because we start from the region-based coexistence series, can we also can our machine learning selected parameter or our based on all these simulations, can we also learn from is our parameter trade-offs reflects the region-based coexistence series? First, like in our experiments, first, relative difference should not be considerable. So you can see that if you have larger considerable, like for example, the specific leaf area index between the early and the late, so you will become more favorable of the early. So the green color is the early. So if you have larger difference in trees, it will more likely favor of the early PFTs. So if you should have the coexistence, you should have a lot larger difference. So this reflects the environmental filtering, which means you have some convergence in strategy, or you have some similarities in your treats or in your strategy. And then also you need to have some difference between these parameters. So you can see from here, if you have small difference, like for a specific area, or you have, for example, here, so it's more favors the late PFTs instead of the coexistence. So you should not have, so you should have some difference, but the difference should at some degree, yeah, cannot be too small. And then when we look at the coexistence cases, means the orange color. So generally the difference between early and late, they are like have intermediate difference in trees. So there are lot, if you have larger difference, it will be early. If you have small difference, you will become late. But for the coexistence, generally you have like intermediate differences. But the conclusion here is like our parameters in the experiments. So we should have not, the difference should not, you cannot have big difference, but you should have some degree of difference, and this reflects the niche-based coexistence theory. So finally, the take-home message from here is like we try different ways. So first, we tried, can we use observed trait relationships to improve the PFT coexistence modeling? The answer is no, but we do note that there are some limitations when we consider the observations. And the second, we try to, okay, we have the control experiment. We build some empirical, like simple relationships. Does this relation enough? The answer is also no, it can improve, but it's not enough. But finally, like we try with machine learning technologies, and we largely improve the model, reduce the model bias, and we largely improve the coexistence cases percentage. So this methodology or this approach can also be used for the other models and for other different systems. And also this machine learning based approach can use to improve the modeling. For example, when we do the parameter sensitivity analysis, we find that for the PFT coexistence, there are more parameters are very important, which means this process is very sensitive. And after we get the most sensitive parameters, we can find out which process does these parameters control. Then we can to go deeper to analyze which process is not represented well in the models. So yeah, basically this study is currently is under revision, and you can find the preprint from the EGU's website. And yeah, finally want to acknowledge this is study supported by the NG-Tropics and which is funded by DOE. Yeah, that's all my talk. Thanks for your attention.